Hi everyone, in this video we're going to solve this differential equation using the method of power series. So this is an initial value problem. We have a differential equation and we have two initial conditions. So the very first step in this problem is to start by letting y be equal to the infinite sum as n runs from 0 to infinity, and here we have c sub n x to the n. And I'm writing small because this problem is super long, so I'm trying to see if we can actually fit it all into one video. Next, we have to take the derivative, and we have to take the derivative twice because there's a second derivative here. So taking the derivative the first time, we get y prime. That's equal to the infinite sum as n runs from 1 to infinity. So every time you differentiate here in this step, you have to shift up. So we're going from 0 to 1, and I'll explain why in a minute. The c sub n here is a constant, so it hangs out. You bring the n down, so you get n c sub n, and then x to the n minus 1. You just differentiate the x as you normally would. So the reason that we shift up is if you were to plug in 0 into y, you would get c to the 0, x to the 0. That's your first term, plus some other stuff. And c to the 0 is a constant, x to the 0 is 1, so you would just get c sub 0. This is a number, so when you differentiate it, it becomes 0. So the 0th term will go away when you differentiate, so you have to start the summation at 1. If we do it again, the same thing will happen. The first term will go away, so we have to start the summation at 2. So we're going from 2 to infinity. And then bringing down the n minus 1 is going to give us n minus 1, c sub n, x to the n minus 2. Good stuff. All right, so now that we have all the derivatives, we just carefully plug them into our differential equation. So we have x minus 1 times the second derivative, so that's the infinite sum, as n runs from 2 to infinity of n minus 1, c sub n, and then we have x to the n minus 2. And then minus x, and then y prime, so y prime is up here. I'm trying to be really careful. It's really easy to mess up in these problems. So we're going from 1 to infinity, and c sub n, x to the n minus 1. And last but not least, we have y, so plus, looks like infinite sum, as n runs from 0 to infinity, c sub n, x to the n, and that is equal to 0. All right, so in this problem, we have some things outside of the sums. We have an x minus 1 here and an x here. So let's go ahead and break this up. Let's distribute the x and then distribute the 1. So distributing the x, we'll get x, infinite sum, as n runs from 2 to infinity of n minus 1, c sub n, x to the n minus 2. And then minus, so distributing the minus 1 will give us an infinite sum as n runs from 2 to infinity, n minus 1, c sub n, x to the n minus 2. Then we have this other x here, which I'll leave out for now, so minus x. You can actually distribute it in, but I'll do that in the next step. N equals 1 to infinity, and c sub n, x to the n minus 1. And last but not least, we have infinite sum as n runs from 0 to infinity of c sub n, x to the n. And all of this is equal to 0. Good stuff. All right, so now we're going to distribute these x's. So there's an x to the 1 here. So when you distribute it, basically you'll have x to the 1 times x to the n minus 2. And what you do is, because the bases are the same, you just add the exponents. So 1 plus n minus 2 is n minus 1. So this is x to the n minus 1. So this will be the infinite sum as n runs from 2 to infinity of n minus 1, c sub n, x to the n minus 1. And then minus infinite sum. N goes from 2 to infinity. Lots of writing and lots of notation. It's like if you copy down one thing incorrectly, boom, the whole thing is wrong. C sub n, x to the n minus 2. Same thing here with this x. We have x to the 1 times x to the n minus 1. So you add the exponents. So 1 plus n minus 1 is n. So we have minus infinite sum. N runs from 1 to infinity. Then n c sub n, x to the n, and then plus the infinite sum as n runs from 0 to infinity of c sub n, x to the n, and all of that is equal to 0. Okay, so now we're in a position where we can do something called shift the index of summation. Let me switch colors here. So basically, we want all of these exponents to be the same. So n minus 1, the n minus 2, the n, and this n. They all need to be the same. So what I like to use is the letter k. So I'll let k be equal to n minus 1. And then you solve for k. So n is equal to k plus 1. Same thing here. K is equal to n minus 2. So you solve for n, so n is equal to k plus 2. Sometimes people say, hey, wait a minute, you can't let k be equal to two different things. It's wrong. We're just being a bit abusive. The k really only exists inside the summation. Remember, this is a summation. If you multiply it all out, there is no n and there is no k. It's just an infinite sum of powers of x. So it's just a placeholder. It's a dummy variable. So it doesn't really matter. And then same thing here. K is equal to n, which is kind of weird. So n is k. It's just a little bit crazy. K is n. Oh, n is k. just for consistency. Okay, so now let's go ahead and make the substitution. So let's see, we have the infinite sum. So n here is 2. So if you take the 2 and you plug it in here, you get k equals 2 minus 1. So k equals 1. So you actually just take the n and plug it into your formula for k to figure out where it starts. So we start at k equals 1, and we go to infinity. And now all of the n's are k plus 1s. So this is k plus 1. And then k plus 1 minus 1 is going to be k. And then c sub k plus 1. And then x to the k. That was the whole point. We wanted it to be x to the k. So again, n is k plus 1. Looks okay. And then n minus 1, well, that's k. And then c sub k plus 1, x to the k. Yep, looks good. Minus infinite sum. So n is 2. Plugging it in here for k, we get in here for n, we get k equals 2 minus 2. So we get k equals 0 this time to infinity. And n is k plus 2. So it's going to give us k plus 2. K plus 2 minus 1 is k plus 1. And then we have c sub n, so c sub k plus 2. And then x to the k. That was the whole point, right? The whole point was to make that a k. I always tell myself that when I get to that step to make sure I'm doing it correct. The whole point is to make these guys k's. So minus infinite sum. This time nothing happens, right? We're just renaming things. So k is 1 to infinity. K, c sub k, x to the k. And then plus, same thing here, just renaming things. K equals 0 to infinity. C sub k, x to the k equals 0. I'm going to go back and just check this second one here because I did it kind of quickly. So let's see, n is k plus 2, looks okay. K plus 2 minus 1 is k plus 1. Yep, everything looks good. Okay, just double checking, looks good. So now we have to make them all start at the same number. So notice that this starts at 1, this starts at 0, This starts at 1. This starts at 0. So the trick is to make them all start at the highest 1, okay? So the biggest number here is 1, so we want them all to start at 1. So what we do is we take this 0 here, we're going to plug it in for the k's, and then we're going to rewrite this sum and start it at 1. Likewise, this 0 here, and this last summation, we're going to plug it in for the k's and then start the sum at 1. So let's go ahead and do that. So we have this sum here starting at 1. It'll make a little more sense once I do it. So k equals 1 to infinity, k plus 1, k, c sub k plus 1, x to the k. And then we're starting this one at 1, so let's just go ahead and start it at 1. And then we'll plug in the 0 and write it at the end. That's typically what people do. So this is k plus 2, k plus 1, c sub k plus 2, x to the k, minus, and then the same thing, just writing it down again, k equals 1. It's a lot of writing. Whenever you're doing these problems for the first time, it's not uncommon for this problem to take you an hour to do, or longer if you get stuck. You might spend, a serious amount of time on this problem. For most people, when they first do these are the longest math problems they've ever done in their entire lives. So here we go. And so now this is wrong, right? We haven't plugged in the 0 yet. So let's go ahead and plug in the 0 for the k here. So it'll be minus, because there's a minus sign here. I've messed that up multiple times. So 0 plus 2 is 2. 0 plus 1 is 1. So we get 2c2 x to the 0. So minus 2c2. And then here again, plugging in 0, we'll get plus c sub 0. And this is equal to 0. Okay, it's equal to 0. So let me just explain what happened one more time. So this piece here, which I'm circling in orange, okay, is a summation starting at 0. So it's the one right below it, which starts at 1, and then here's the 0th term, the negative 2c2. So this negative 2c2 here, together with this summation starting at 1, are equal to this, right? This is the 0th term. This is the rest of them. So this is the sum from 0 to infinity, and it's right here. Here you see it from 0 to infinity in one piece. Here it's from 1 to infinity, and then you have the 0th term attached. Same thing here with this last summation. This summation starts at 0, but below it you see the summation starting at 1, and it's missing the 0th term, but the 0th term is over here. Okay, so now we can finally combine these into a single summation. Okay, let me switch colors here. So we have the infinite sum starting at k equals 1, going to infinity. I'm going to use a bracket here. And I'm going to factor out an x to the k from every single one of these. So we have parentheses k plus 1, k, c sub k plus 1. Wonder if anything cancels. No, nothing looks like it cancels, unfortunately. Not yet. Minus k plus 2, k plus 1, c sub k plus 2. Okay, and then minus, I'm just going down the line, just looked at this one first. Now we looked at this one, everything still looks okay. Minus k c sub k, and then plus c sub k. Wow, ridiculous. Ridiculous. X to the k. And then we have these little dangling parts, minus 2c2 plus c sub 0, and that's equal to 0. Good stuff. All right, so now what you do basically is you do an infinite version of equating coefficients, right? Because this is really 0, this is really 0 plus 0x plus 0x squared plus, dot, dot, dot. So if this is true for all x, all of the coefficients must be 0 via matching. So we take this entire piece here, and we go back to yellow, and we set it equal to 0. So we have k plus 1, k, c sub k plus 1, minus k plus 2, k plus 1, c sub k plus 2, my handwriting is deteriorating, minus k, c sub k, there it is, it's better now, plus c sub k, and this is equal to 0, 4, and you want to start here. So this tells you where to start, which is super important. So for k equals 1, 2, etc. This whole thing is a constant term, so that whole thing is equal to 0. It's important to set the entire thing equal to 0 because the whole thing is a constant term. All right, let's focus on this here. So we have to solve for the one now that has the highest subscript. So we're going to solve for c sub k plus 2. So to do that, I'm going to do it in steps. So first I'll keep this piece here on the left. So negative k plus 2, k plus 1, c sub k plus 2. Then we're going to move everything else over to the right-hand side. So this one here is going to go to the right-hand side, so it'll be negative k plus 1, k, c sub k plus 1. And then this one's going to go to the right-hand side, so plus k, c sub k, and then this one's going to go to the right-hand side, so minus c sub k. All right, now we're going to divide everything by k plus 2 and k plus 1 and a negative sign all at once. I'm trying to think if there's an easier way to do this. Maybe not. Let's just do it. So c sub k plus 2 is equal to, and again, you always solve for the one with the highest subscript. So in this case, it was c sub k plus 2. Let's think very carefully here. So we're dividing everything by negative k plus 2 and k plus 1. So in the first term here, we're going to lose the negative k plus 1. So it'll just be k over, and then just k plus 2, I believe, because the negative k plus 1's cancel. Yeah, very good. And we're left with c sub k plus 1, right? So the negative k plus 1 will cancel with this negative k plus 1, and we're just left with k over k plus 2. And then over here, I'm going to kind of keep it together here. I'm going to pull out the ck, so I'm going to write this as, well, we're dividing by all of this, right? So it'll be negative, so this will turn into a negative. And I'm going to write it like this, k minus 1 ck, see how I did that? I pulled out the ck. The negative is coming from this negative we're dividing by. And then on the bottom here we have k plus 2, k plus 1. Very good. Good stuff. Good stuff. All right, and this is valid for k equals 1, 2, 3, etc. So this is called a recurrence relation. Okay, a recurrence relation. This comes up in other areas of math as well, like if you ever study discrete math and you study counting problems, you can use recurrence relations like this one, or not like this one, easier ones, to solve counting. Here, same deal. 2 is bigger than 0, so we'll subtract c naught. And so c sub 2 is equal to 1/2 c sub 0. I'm going to put this in a box as well. This is also very useful. Okay, so now we're going to try to finish the problem. And we're almost there, not quite. We're about halfway through. So the final answer, this is really important. Let me do it up here on the top right. Let me scroll up, give us some more room. So the final answer to this problem is y equals c sub 0 y1 plus c sub 1 y2. That's the final answer, where the c sub 0 is from the power series and this c sub 1 is from the power series. Now, I say final answer, after we do all of this, we still have to go back and use our initial conditions to, to figure out the c's. But before we get there, we have this. And so what we're going to do is we're going to exploit this fact. Notice that if c sub 0 is equal to 1, like if we make it equal to 1, if we decide to do that, and c sub 1 is equal to 0, then that would give us y equals y1. So whenever this happens, we get y equals y1. So we get one of our answers, one of our linearly independent solutions. If c sub 0 is equal to 0 and c sub 1 is equal to 1, Notice what happens. The first term vanishes, and we get y equals y2. And so we get our second linearly independent solution. This is a name. I made this up. It's called the indirect approach. It's a totally made up name. I've given it this name because doesn't have a name. So the direct approach is you just plug in numbers and hope for the best, hope that you find a pattern. This is a little bit easier because if you could do this, then this will give you one of the answers and you can focus on the pattern. If you do this, this will give you the other answer. Once you have both answers, you go back in here and plug them in and you use your initial condition. So I just memorize it. Whenever you do this, you get one of your answers. If you do this, you get the other answer, always. So you do it twice. So let's do it. Let's do the first one to find y1. So first, we'll do C0 equals 1, C1 equals 0. I'm going to underline this just so we have some organization. Now we have to find C2. But we can use this formula here. So C0 is 1. So when you plug in 1, you get 1/2 times 1. So you just get 1/2. I'm going to put that in a box. Okay, that's going to go in a box. All right, now let's find C3. So to find C3, we'll use our recurrence relation. So when k is 1, notice how I write down k is 1. That's how I don't mess up. C sub 3, right? 1 plus 2 is 3. So k is 1. So k is 1. So this is equal to, so 1 over 1 plus 2 is 3. And then 1 plus 1 is 2, so that gives us C2. And notice 1 minus 1 is 0, so the rest of it goes away, right? You plug in a 1 here for the k, it vanishes. C2 is 1/2, so we get 1/3 times 1/2. I'm skipping a step, so we get 1/6. Okay? You can think of 6 as 3 factorial, by the way. Is that going to be helpful? Possibly, right? Possibly. Let's do another one. K equals 2. When k equals 2, we get 2 plus 2, so we get C4. It's an explosive in movies. So k is 2, so you get 2 over 2 plus 2. So you get 2 over 4, which is 1/2, skipping some steps. 2 plus 1 is 3, so we get C3. And C3 is 1 over 3 factorial. So you have 1/2 times 1 over 3 factorial. That's 1 over 3 factorial is 6. So that's going to be 1 over 12, I believe, right? 1 over 12. Let me just make sure we did that right. K equals, oh, we're not done. Yeah, we're not done here. So that's correct so far. Minus, I messed up. So minus, right here, the rest of it. So plugging in 2 is going to give us 2 minus 1, which is 1. Then we have our C2. And on the bottom, we're plugging in 2. So we get 4 times 3. So I caught my mistake because we got 12. And I was thinking, okay, if we have a 3 factorial here, we're hopefully going to get something else with the factorial. So I realized here that we still need to deal with this minus. So this is equal to, so it's 1 over 12 minus C2 is 1/2. So it'll be 1/2 over, and then 4 times 3 is 12. So this is 1 over 12 minus 1 over 24. So you can think of this as 2 over 24 minus 1 over 24. Ridiculous. So this is 1 over 24, which is 1 over 4 factorial, which feels a lot better than my incorrect answer. So this is C4. So now you see, it looks like we have a pattern, right? We have 1 over 3 factorial, 1 over 4 factorial. So now maybe we're in a position to go ahead and write down y1. So y1 is equal to, so what is y1? Where do you get it? If you go back to the very beginning of the problem, okay, the very, very beginning, right here, this is the very beginning, y equals this infinite sum. That's the answer, right? So you just write it out the long way. So C0 plus C1x, etc. So let's go ahead and carefully do that. This will be C0 plus C1x plus C2x squared plus C3x cubed plus C4x to the 4 plus dot dot dot. It's equal to. So C sub 0 is 1. C sub 1 is 0, so it's gone. C2 is 1/2, so it's plus x squared over, let's write it as 2 factorial. C3 is 1 over 3 factorial, so it'll be plus x cubed over 3 factorial. And the next one is x to the 4 over 4 factorial, etc. So this is y1. We are almost there. So that is y1. Let's find y2. Let me switch colors here so we can see a little bit better. To find y2, we'll do c0 equals 0 and c1 equals 1. Right? We'll flip our conditions. And as before, now we have to find c2. So c2 is given by 1/2 c0. So c0 is 0, so c2 is just going to be 1/2 times 0, so it's 0. So C2 is also 0. I'm going to put that in a box. To find C3, as before, we will use our recurrence relation. So when K is 1, we plug it into our formula. So we get C3 equals, so we're going to get 1 over 3, and then C2, 1 plus 1 is 0. So C2 is 0, so we just get 0 minus, and then K is 1, so we get 1 minus 1, which is also 0. Okay, interesting. So C3 is equal to 0. That's quite interesting. Okay, so C3 is equal to 0. Huh, okay. Let's see what happens when K is equal to 2. That'll give us C4. So we'll get 2 over 4, right? 2 over 2 plus 2 is 2 over 4, so it's 1/2. And K is 2, so that'll give us C3. And then minus, and then plugging in 2's over here, we'll get 1 times C2. And plugging in 2, we'll get 4 times 3. But wait a minute, C3 is 0. And so is C2. So C4 is actually 0 as well. Interesting. So C4 is 0. That's quite interesting. Let's mentally think about what happens when we plug in 3. If we plug in 3, we're going to get C4, which is 0. And we're going to get C3, which is 0. So it looks like everything else is going to be 0. So it looks like C5 is equal to C6, which is equal to everything else, and they're all equal to 0. That's really good news. So Y2, writing it out the long way, is C0 plus C1x plus C2x squared plus etc. So C0 is 0, C1 is 1, so we get 0 plus 1 times x plus 0 times x squared plus 0 times x cubed plus dot dot dot. So we just get x. So y sub 2 is just equal to x. That's super awesome. All right, let's write down our general solution. So y is equal to, so it's going to be, I'm going to switch now to c's. So the answer to the problem without the initial conditions is going to be C1, I'll use a big C, y1, so it's going to be this here, 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot 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 plus big C2x. I know initially I used the little c's, and I did that on purpose just to indicate that they are from the power series up here, you see. But in general, the answer to a second order DE is big C1 Y1 plus big C2 Y2, where you find these guys by using your initial conditions. It turns out that big C1 is equal to little C0 from the power series, and big C2 is equal to little C1 from the power series. So we exploit that fact as we just did. So our initial conditions, let's go ahead and write them down here so we can use them. They were y of 0 equals -2 and y prime of 0 equals 6. let's go ahead and use these. So I guess let's find the derivative. So y prime, so the c1 hangs out, it's a constant. The derivative of 1 is 0, so we just get 2x over 2 factorial plus 3x squared over 3 factorial plus dot dot dot, plus the derivative of x is 1, so we just get c2. All right, let's impose our conditions. Doing the first one, so y of 0 is -2, so using it here. So y of 0 will be equal to, let's see, c1, parentheses 1, everything else is 0, so because there's a bunch of x's there, plus c2 times 0. And this is equal to -2. This means that c1 is equal to -2. I'm going to put that in a box. That is not just an accomplishment, that is a huge accomplishment. And then so y prime of 0, this is nice because everything here is 0 right after the c1. So times 0 plus c2, that's equal to 6. And hurrah, c2 is equal to 6. So now we can plug them back in and see what happens. So y is equal to, let's see, c1 is -2, 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot 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 plus, and then c2 was 6, so 6x. So this would be the answer, but I'm pretty sure the problem wants us to write the final answer in terms of familiar functions. So if you remember from math, e to the x is equal to 1 plus x squared over 2 factorial, plus x cubed over 3 factorial, etc. So we almost have that here. We're missing the x. So here's what we do. We just put it there like this. So -2 parentheses 1 plus x. You might say you can't put it there. Yes, we can. Check this out. So you write it down because you know you want it to be there. So you just put it there, right? But you can't just put it there. You have to be correct, right? It's math. It can't be wrong. So what did we really put there? Well, we wrote down x, but notice the parentheses on the outside. We really put a -2x. So we have to get rid of it by adding 2x, and then we still have our 6x over here. Again, -2 times x is -2x. So in order to make these true, you have to add a 2x here because 2x plus -2x is 0. So this is equal to -2, and here's the beautiful part. Now all of this is e to the x, right? It becomes e to the x, and then 2x plus 6x is 8x. And that would be the final answer to the initial value problem. And that is the correct answer. I actually have the answer here, but I don't have the work. So we did it. That's actually correct. Long video, 33 minutes. If you're still watching this, congratulations for watching the longest math video you've probably ever watched, maybe. It's one problem. But it's a good problem, and it should take you, like, once you learn how to do these, it might take you maybe, half an hour. That's how long this video was. But if I was doing this on my own, I'd probably go a little bit faster, even though I was rushing you to the end. I didn't want to turn this into an hour-long video. Typically, like if I do this in a classroom, this problem would easily take a full hour to do. So yeah, not too bad once you know how to do it. And I think the key step is up here. This indirect method, this is key, right? I just memorized this. So once you get to this step here, right here, where you have your recurrence relation, and you have this condition here and this condition here, you basically do this: C0 equals 1, C1 equals 0, get one of your answers, and then just do this: C0 equals 0, C1 equals 1, and then get your other answer. And then after you do that, you write them like this, okay? C1 times your first answer plus C2, big C's, okay, times your first answer plus big C2 times your second answer. Take the derivative, use your conditions, and then after that, it's not too bad. There's this little sneaky, beautiful trick at the end, but it's not too bad. I hope this video has been helpful. Good luck.